what we did in last discussion, I'd like to just quickly summarize it. So what we did, we tried to make sense of, at least have an intuitive picture of different kind of maps. Okay, so we know what is the meaning of having a map from R to R. Okay, so there are two important things. Number one, map, and the graph of a map. So these are two different things that we need to keep in head actually. So if you have a map from R to R, I know if I'll talk about the graph of it, okay, the graph of it, for representing the graph of it, I need, you know, a two-dimensional plane actually. Okay, so what essentially we are saying is that from this domain, you know, f is operating onto entire R, maybe the some part of R, and turning and throwing that into the R actually. Okay, so if you want to graph it, okay, so what you need to do, you need to plot all of the points which are of the form, say, x and f of x. Okay, so in other words, if this is the domain, so what we are doing, to each point in the domain you are providing the height actually. Okay, and you know, so for example, if this is the point x, okay, some x will be some x star, then this value is what you call f of x star, the height f of x star. But since this point lies in two dimension, okay, so wouldn't that be better if I use rather than so let's do once again. So we said that if you have a map from R to R, okay, so when we see the graph of such a maps, you're going to get a curve in two dimension. Okay, x, y plane. If I say, say this bit is the domain of the graph, okay, then what this f is doing, it's taking a point, each of the point from this domain and assigning it a height actually. Okay, assigning it a height. And what is that height? F of a actually. So the representation of these points become a and f of a. Okay. So for each point a, I have a point in two dimension whose coordinates are a and f of a, where the f of a represents the height of the function. Okay, the value of the function evaluated at a. By the way, if I want to treat this graph, I can have another way to look at basically this graph, and that another way could be that let's treat this. Let's try to define a map basically that takes each input from, what do we say, this domain, and gives us a point on this curve actually, or on the graph. Okay, so I can say that I have a map. For example, let's call it capital F or whatever, that takes, so that is a map from R to R2, that is doing what? That is taking the input A and giving me the corresponding point on the graph actually, A and F of A. Okay. So what simply this A can do, so in other words, when you have such kind of a graph, you not only have a map from R to R, but looking at this graph, you can also define a map from R to R2 actually. Okay. And you can do the precisely same thing for a map from, say, R2 to R2 to, for example, R. Okay. R2 to, for example, R. So the picture that we saw, that by R2 I mean, okay, maybe as some part of R2, that's a domain of the function, and to each point here, say x, y, z plane, I'm assigning a height. Okay, relevant to the value of z actually. Okay. And what would be the coordinates of this? So it's going to be, you know, for example, if this is AB, okay, the coordinates of this is going to be A, B, and F of A, ordered pair of A. Okay, so AB is the kind of height. And I know that if I collect, so if I take all these points and assign them, you know, assign the heights to them, and combine all of those points, so I'm going to get what you call a surface. Okay, roughly a surface. But this is, you know, the surface is the graph of such kind of map. Okay. That's another way to look at it. But I know that as I described, you know, relationship between this line and the graph through a map F, which I can treat as a map from R to R2, I can have a similar kind of stuff here as well. So I can say that I have a map F, the graph map actually, okay, that takes input what? From R2, takes, you know, from the domain, part of the R2, and throws it onto a point on the surface actually. Okay, whatever surface means, we'll technically define it afterwards. Okay? So that's going to be a map in R2 to R3 actually. Okay? So there are two things. Number one, if you have a map, okay, you know, I can make a graph of it, and I can treat that graph, or corresponding to that graph, I can define a graph map. That's going to be a map from R2 to R2, but I can, similarly, I can also define a map from R3 to R3. So in other words, I take you know, for example, some chunk of points of surface, and I associate them with another chunk of points on the surface actually. Okay, so point to point. So I can treat such kind of maps as maps that takes the inputs from R3, but not from all R3, or from this surface actually. Okay, and relating it to another, what do you call, surface. So this would be kind of an example of having a map from R3 to R3. Okay, but we also talked about an example that, you know, so if we have a map from R3 to R3, another way to look at it is going to be that we're going to treat it as the vector fields actually. Okay, so in other words, that you have this surface, but onto this surface, to each point you are assigning, you know, a vector field. So we'll talk more about the vector fields in our, you know, physics discussions actually. Scalar fields will be always talking about this actually. So the good thing about the physics 2 is going to be that it's going to be the really applications of what you are learning here. Is it making sense? Yes. So similarly, you can have, for example, if I have a map from R3 to R, okay, and then if I want to see the graph of it, so I need to go in 4 dimension actually, because each point on that, what do you call, hypersurface. So whenever you have something in higher dimension than 3, you call it a hypersurface. So if I have a hypersurface, it's no more going to be a surface, because surface is something that is associated with 3 dimension. So what would be the meaning of having a surface in 4 dimension or 5 dimension? So should we call them surface? That would be the first question actually. But so we call them hypersurfaces actually. I get a good point. Okay. So to describe that hypersurface, which kind of which is kind of seen as a graph of a map from R3 to R, okay, you need 4 coordinates actually, so you'll be in the 4 dimensions. Is it making sense? Alright, so this was something it. Now I would like to next talk about, you know, the first stuff that is about the limits, that how to define limits actually. So we defined the limits in one dimension, okay? And now I would like to extend that idea and I would like to define the limit in higher dimension. So in other words, how to compute the limit of a function when f is not a map from R to R, but Rn to Rm, and n and m can be your choice.
Actually, sir, so about the limit neighborhood is deleted neighborhood and function neighborhood.
No, we will define it precisely. But before that, I would like to begin with intuition. So I would like to show, so as one dimension in our previous discussion helped us to picture things in higher dimension. So similarly, I would like to talk about the limit in the one dimension. Okay, and then I would like to, talk about its picture in higher dimension. Okay, because if you understood that, you can really extend it very well. Okay, so we know about the limits. So limits have something interesting with them. So how do you describe the limit in the one dimension? Okay, so I'm not talking about the computation. We all know how to compute the limits. Okay, so I'm talking about the notion of the idea actually. So imagine if I have a curve. Okay, maybe I can make it from Desmos. Okay. Let's go to the Desmos. So imagine I have a curve. So give me, choice of your curve. For example, let's take say f of x equal to. Okay, let's take your orthogonal curve Q. Okay, and I want to compute this. Maybe square. Okay, and I want to talk about make sense of this actually. Limit x goes to 2, f of x would be, what is the meaning of it actually? Can we really see, can we get a feel of it there, what does it say? Okay, so I would like to give the standard notion and then I would like to talk in detail about it, that what does it mean. So I plotted f of x equal to x square. The next thing that I would like to do is plot an arbitrary point on x-axis. So for that, what I'm going to do, I'm going to take, say a symbol C0. So I know that this is going to be a point on x-axis. Okay, and to this C, I'm assigning a slider. So the good thing about the slider is that this C is now arbitrary. Okay, so in other words, as you move the value of the C, this point would change that. Okay, so I would like to treat this point, this point as input point actually. Okay, so that's my input. And the interval at the moment, for example, so I can, if I wish, I can extend it more, but okay, for our purpose, 10 to minus 10 is enough actually. Okay, and then I would like to plot the point, the output corresponding to this actually. Okay, so how can I plot the output corresponding to this? So let's plot C and say f of C. Okay, and now what will happen that if I will move my inputs, the outputs are moving as well. Okay, my outputs are. So what is the meaning of this movement? So wherever you will place your point, so it's going to tell you the input, and this upper point is telling you kind of the output of that function. Okay. So our classical understanding, something that you have started learning from your intermediate classes actually, that what is the meaning of, as x gets closer to 2, the value of the function will get closer to 4. So that's what is your classical understanding actually, that okay, if I, for example, say that as my inputs are getting closer and closer and closer and closer from the left of the 2 to the 2, the outputs are getting closer and closer and closer. So what? 4 actually. It's getting closer to 4. So because I'm kind of computing the left can also approach to this 2 from the right actually. Okay? So as we are getting closer and closer and closer to 2, the corresponding outputs are getting closer and closer to 4. Okay? You can really see that. Is it making sense?
Yes.
So that is our intermediate level understanding. I just quickly recall it. But I want to grow up now. I would like to come to the university level now. Maybe the calculus 1 or. So how many of you people have seen this epsilon delta definition for limit actually?
We have seen, we have read, but we have not visualized like this.
Okay, so you have read it, but you haven't visualized it. So what actually you would like to do is this. Let me give you a rough picture and show that how does it works. So imagine I have any graph. Okay, so I have this graph. And I'm asking the question, and I have a fixed point, A. Okay. And I have, a value corresponding to A. I can have value corresponding to A, but it's not necessary that you should have a value corresponding to A, but you have something A corresponding to A. So you can call it, okay, this is the value of the A evaluated at A. Okay? So what essentially I want to do, by the way, this value is corresponding to a value here. Okay? Okay? It corresponds to a value. Maybe if you want to call it, okay, if I wish you can call it A, but if I wish I can call it L as well. So that's some value L. Okay? So that's some number L actually. Okay? So what I want to show this. As x gets closer to A, as you get closer to A, the value of the function will get closer to the limit L actually. Okay? Now I'd like to give you a quick, brief description of that actually. In other words, this definition is trying to, you can already realize that, you are kind of wrestling with this notion of nearness actually. Inputs want to get near to something, and you want make output to get near to something actually. Okay? So if this value is L, okay, and I take some bunch of values, okay, above and below L, okay, so I don't know how much this length is, so it's pretty small, so let's give it L minus epsilon, and let's call it L plus epsilon. This L minus epsilon is going to have an impact. Okay, so we are talking about this value L plus epsilon, L minus epsilon, and L plus epsilon. Okay, so in other words, what we are saying that if, and epsilon is what? It's your choice actually. It's your, how much closer you want to get to the L. How much closer you want to get to this number, okay, or this, what do you call, point L actually, okay, the value L, okay. So this is my choice. Epsilon is in my control actually, okay. So I want L to stay in this interval, okay. I want outputs in this interval, okay, whose length, whose radius is epsilon, which is like a ball that we did in the ball. Okay. The question is, if you want to stay near to this value L, up to this extent, epsilon, okay, and epsilon could be whatever you like. You need to control the inputs. So where should be my inputs on this line, so that, in other words, what interval should I choose in such a way that if in that interval, if I take any value and if I choose any value, the outputs are going to be between this piece actually. Okay? And the outputs being on this piece means that the outputs are in this interval. Okay? As I am.
Yes.
So in other words, I want to stay in the neighborhood of this point. Really, really near to this point actually. The question is, where should be your input? If the limit exists for this interval, or more precisely this interval, you can find always the smallest enough interval with some radius delta such that if you see the outputs of, okay, maybe this is a plus delta and this is a minus delta, and if you take all these points in this interval and see their corresponding outputs, they are in your required interval actually. I get the point. So so if this limit exists, in other words, if you can get arbitrarily close to L, you can always find the set of inputs, okay, around A in such a way that if you take those values and substitute into the function, the outputs is going to be in the neighborhood of L. Okay, this number L. Okay. For every epsilon, you can always find a delta. In fact, not only this delta, but instead of this delta, if I choose this delta, and I consider all outputs, okay, they are still in my allowed, whatever you call it. You can have many deltas. Are you getting the point? So for a set of values, okay, for the set of outputs, you can always find a set of inputs in such a way, okay, that the outputs of this small interval stay in your required interval. Okay. This seems a bit abstract, but what does simply it says that this is a kind of a function which is taking the near points and throwing them on the near points on the curve actually. So it is respecting the nearness, and that's precisely what is the definition of continuity actually. So continuity is what? Good thing about the continuity is, it always throws, it always spits out the nearest points to the nearest points actually. Okay, so it can't throw the two near point to really big difference actually. Okay, I get the point. This is making sense a little bit. So for each interval, you can find such a delta, and you can really see it here. Okay, so here's the thing. So imagine you have this f of x equal to x squared function. So I have f of x equal to x squared function, and my epsilon is 0.5. Okay, my x star is 2. Okay, by x star I mean A. Okay, whatever the role of A is playing here is here is x star actually, and epsilon is 0.5, and L is 1. Okay, at the moment, but if I wish I can vary the L as well actually, but let's keep it 1 for now. Okay, so what does it mean? Here's the thing. So if I am in the neighborhood or near to this point, is the outputs of that neighborhood, okay, which is around this point, going to be in the neighborhood of 1, which is here. So if this is 1, okay, this is 1, and epsilon is what, 0.5. So this is 0.5, and that's 1, 0.5 actually. Okay. What I want to do, I want to say, if my inputs, if you fix this epsilon, and you say that, okay, I want to stay near in this, to this value in this interval. So the question is, what should be the set of values from the inputs in such a way that if you consider their outputs, the output stay really in your required interval actually. Okay? See that whether we can find it or not. So what we can do, that if you bring these points together. Okay, so let me say this. So currently this situation is telling you if the limit x goes to f of x equal to 1, the answer is no actually. Okay, and I can see it. Okay, so the interval is here, and no matter how small or big I make this interval, I'll never get into this interval actually. So let me show you that how actually. So let's variate the delta. So the delta is going to do what? So see, I want to get the values in this interval, in this part of the segment actually. While here I'm not in this part of the curve actually. So in other words, maybe I'm doing something wrong. And that wrong is that I need to variate in this value L. So let's variate L to 4 actually, and let's see what happens. Can we have this now? So what I want now, so the question is changed now, and I would like to do this. Limit x goes to do f of x equal to 4 actually. So in other words, I have 4, that's 3.5 and that's 4.5 actually. So I'm talking about this chunk. So that for this chunk, can I find some inputs around 2 whose outputs always stay within this part of the curve actually?
Yes.
If you can find such a small interval, that means that limit exists. Okay. So let's see that if this delta works currently, whatever this delta is, the answer is no, because for this, the one output is here, which is outside this part, and the other part output is here. So what I need to do, I need to shrink this, and let's see that whether I can get into my required interval or not. Okay. Okay. Let's make it more smaller, look small. So still I'm outside that part of the curve. Okay. And let's make it even more smaller. Now I'm inside. Can you see this? Can you see this? So for this epsilon, in other words, for this epsilon around, so if you want to stay on the outputs around this output 4 on this curve, you need to choose the values, of the inputs from this small interval, okay, whose, what do you call, say, length is 0.1. Yeah, the radius is 0.1. Can you see? So if you can always find, for every choice of your interval, if you can always find such a delta, that means that you have it. Is it making sense? Okay. And now I would like to invite you to think of the same thing but in higher dimension. Okay. So I have a set of outputs onto the curve. For that, I would like to find the set of inputs such that if I apply my f onto that set of input, the outputs are within my range actually. Outputs are there wherever I want to live actually, wherever I want to put them. Okay, so that's what is the key thing. Okay, it's a bit abstract, but it's not that difficult. So essentially you are saying, I want to stay, this much closer onto the curve. So I want to control